Oh, there's something in my chest that I can't hide. When feelings get involved, I'm terrified. 'Cause I've been here before and said goodbye. Oh, are you the one when I try look I wish I'd find? Oh, how can I love when I've been hurt 100 times? For you I'd give it one more try. Turn away and wrestle with my doubts. Oh, I leave them all behind, but don't know how. Bury my head deep within the crowd, but I'm reaching for your hand to pull me out. Oh, are you the one when I try look I wish I'd find? Oh, how can I love when I've been hurt 100 times? You can see straight through my life. Oh, there's something in my chest that I can't hide. When feelings get involved, I'm terrified. 'Cause I've been here before and said goodbye. Oh, are you the one when I try look I wish I'd find? Oh, how can I love when I've been hurt?
Okay, sorry about the delay, folks. Here we are. Where are my captions? Oh, they ran out again. All right. All right, easy enough to fix. Let me do that real quick. I really need to find a new captioning software. Go ahead and fix it in this screen as well. So that if I game later, it'll already be done. Alright, so we are on to chapter 2 of the Time Travel Handbook. So I don't see any reason to delay. Let's just jump straight on into it. I'm going to sit back, get comfortable here. Do I need to have spectacles for this? This type is a lot bigger than in the last book. Okay. All right, Chapter 2, Relativity and Space-Time Curvature, from Entropy to Time Reversal, Invariance, and Beyond. So hopefully this one's not quite as heavy on the physics formulas, because it's just really not my thing. I mean, just because I haven't studied it. Not that I don't enjoy it, I just haven't studied it, so I don't understand a lot of the formulas. So, all right, here we go. So we've got two quotes to begin with. In science, one tries to tell people in such a way as to be understood by everyone, something that no one ever knew before. But in poetry, it's the exact opposite. Paul Dirac, 1902 to 1984. The second one is mathematicians are like Frenchmen. Whatever you say, they translate into their own language, and it means something very different. Attributed to Goethe. Goethe. I know it's German. My German is not great, though I have studied it, so it should be something like Goethe. Anyway, the desire for a mechanical time travel device takes us into the realms of relativity and space-time curvature. In the Star Trek, I saw Trek and read Wars. Sorry. I'll get lined out here. In the Star Trek television and movie series, the USS Enterprise would achieve warp speeds, where faster-than-light travel strained the dilithium crystals as the Enterprise sought to gain its destination as fast as possible. However, in the Star Wars series by George Lucas, the spaceships are capable of jumping instantly from place to place, from solar system to solar system, rather than running at warp speed. They are jumping through hyperspace. This is not faster than light, it is other than light. It is traveling by jumping from dimension to dimension and transcending time and space at the same time. That's not really true. In the Star Wars, it still takes time to travel. It's not an instant jump, but whatever. No point whose coordinates can be calculated is too far away. It can be reached in an instant. It is time travel as well. To conquer hyperspace, an in-depth knowledge of relativity and space-time curvature is required. Oh, joy. Okay. From entropy to time control. Entropy is the scientific term for the degree of randomness or disorder in processes and systems. In the physical sciences, the concept of entropy is central to the descriptions of the The descriptions of the thermodynamics or heat transfer properties of molecules, heat engines, and even the universe as a whole. It is also useful in such diverse fields as communications theory and the social and life sciences. Entropy was first defined by the German physicist Rudolf Clausius in 1865, based in part on earlier work by Sadi Carnot and Lord Kelvin. Clausius found that even for quote-unquote perfect or completely reversible exchanges of heat energy between systems of matter, an inevitable loss of useful energy results. He called this loss an increase in entropy and defined the increase as the amount of heat transfer divided by the absolute temperature at which the process takes place. Because few real processes are truly reversible, actual entropy increases are even greater than this quantity. This principle is one of the basic laws of nature known as the second law of thermodynamics. The first law of thermodynamics states that energy is conserved. No process may continuously release more energy than it takes in, or have an efficiency greater than 100%. The second law is even more restrictive, implying that all processes must operate at less than 100% efficiency due to the inevitable entropy rise from the rejection of waste heat. For example, large coal-fired electric power plants inevitably waste about 67% of the energy content of the coal. Other heat engines, such as the automobile engine and the human body, are even less efficient, wasting about 80% of the available energy. An imaginary perpetual motion machine would have to defy these laws of nature in order to function. Such a machine, having its own output as its own energy source, would have to be 100% efficient to remain in operation. Friction always makes this impossible, for it converts some of the energy to waste heat. The arrow of time. Another manifestation of entropy is the tendency of systems to move toward greater confusion and disorder as time passes. Natural processes move toward equilibrium and homogeneity rather than toward ordered states. For example, a cube of sugar dissolved in coffee does not naturally reassemble as a cube, and perfume molecules in the air do not naturally gather again into a perfume bottle. Similarly, chemical reactions are naturally favored in which the products contain a greater amount of disorder, entropy, than the reactants. An example is the combustion of a common fuel. Such reactions will not spontaneously reverse themselves. This tendency toward disorder gives a temporal direction, the arrow of time, to natural events. A consequence of nature's continual entropy rise may be the eventual degrading of all useful energy in the universe. Physicists theorize that the universe might eventually reach a temperature equilibrium in which the disorder is at a maximum and useful energy sources no longer exist to support life or even motion. This heat death of the universe would be possible only if the universe is physically bounded and is governed as a whole by the same laws of thermodynamics observed on Earth. The concept of entropy also plays an important part in the modern discipline of information theory, in which it denotes the tendency of communications to become confused by noise or static. The American mathematician Claude E. Shannon first used the term for this purpose in 1948. An example of this is the practice of photocopying materials. As such materials are repeatedly copied and recopied, their information is continually degraded until they become unintelligible. Whispered rumors undergo a similar garbling, which might be described as psychological entropy. Such degradation also occurs in telecommunications and recorded music. To reduce this entropy rise, the information may be digitally encoded as strings of zeros and ones, which are recognizable even under high noise levels, that is, in the presence of additional unwanted signals. The onset and evolutionary development of life and civilization on Earth appears to some observers to be in conflict with the second law's requirement that entropy can never decrease. Others respond that the Earth is not a closed system because it receives useful energy from the sun, and that the second law allows for local entropy decreases as long as these are offset by greater entropy gains elsewhere. For example, although entropy decreases inside an operating refrigerator, the waste heat rejected by the refrigerator causes an overall entropy rise in the kitchen. Life on Earth may represent a local entropy decrease in a universe where the total entropy always rises. Ongoing work by the Belgian chemist Ilya Prigogine and others is aimed at broadening the scope of traditional thermodynamics to include living organisms and even social systems. The experience of time or of time duration has received great attention in literature and philosophy. The experience varies among individuals and, because of its subjective nature, may appear to be inconsistent even in one individual. In scientific work, a numerical measure is used to order observations of events. If now is assigned the numerical value 0, then it is usual to assign earlier times negative values and later times positive values. To obtain a time scale, some periodic phenomena that has repetitions occurring at a uniform rate that may be subdivided and counted must be used. Before the 20th century, it was assumed as self-evident that a single uniform time scale existed. For two events that are widely separated in space, it has been assumed that there is no difficulty in defining the meaning of the concept of simultaneity, namely, if to one observer the events appeared to occur simultaneously, then all the other observers would agree that the events were indeed simultaneous. Albert Einstein, however, early in the 20th century recognized that because of the universal constancy of the speed of light, the measurement of time depends on the motion of the observer. Considering events A and B separated in space, which appear simultaneous to one observer, to another observer then who is in motion relative to the first, the event A may occur before or after B, depending on the direction of the relative motion between the two observers. Thus, in the modern view, time is no longer absolute, but dependent on the relative motion of observers making the time measurements. According to the theory of relativity, time is but one aspect of a more general four-dimensional space-time continuum in which events occur in the universe. Time and space are different aspects of this underlying four-dimensional continuum. Frequently, time is described as a fourth dimension. Timescales. From earliest times, the rotation of the Earth, or the apparent location of the sun in the sky, has been used to establish a uniform time scale. In order to specify a date, using the apparent motion of the sun as a time scale, days must be counted from some reference date. In addition, a clock is used to measure fractions of a day. Time derived from the apparent position of the sun in the sky is called apparent solar time. Because of the eccentricity of the Earth's orbit around the sun and the inclination of the Earth's rotational axis to the orbital plane, apparent solar time is not a uniform time scale. These effects can, however, be calculated and corrections applied to obtain a more uniform time scale called mean solar time. Universal time, UT0, is equivalent to mean solar time at the Greenwich Meridian, Greenwich Mean Time, or GMT. Observations of the apparent motion of a distant star may be used to obtain yet another time scale used in astronomy called sidereal time. Additional small deviations from the uniformity of UT0 may be traced to small effects such as the wandering of the Earth's polar axis and other periodic fluctuations of the Earth's rotation. Accounting for these effects leads to additional, even more uniform time scales, UT1 and UT2. Ephemeris time is determined by the orbital motion of the Earth about the Sun and is not affected by fluctuations in the Earth's rotation. Astronomical observations may be used to determine ephemeris time to an accuracy of roughly 0.05 seconds, averaged over a 9-year period. The invention of the quartz crystal oscillator and of the atomic clock makes possible the measurement of time and frequency more accurately than any other physical quantity. Thus, in addition to astronomical time scales, there are other time scales such as atomic time, AT, based on the microwave resonances of certain atoms in a magnetic field. Counting the cycles of an electromagnetic signal in resonance with cesium atoms provides an accuracy of a few billionths of a second over intervals of a minute or less. Since about 1960, a number of laboratories around the world have cooperated in comparing their atomic timescales, leading to the formation of a weighted average of the various atomic timescales, which is now disseminated to the public as Universal Coordinated Time, UTC. In order to keep UTC in agreement with the length of the day, seconds are occasionally added to or deleted from the atomic timescale, a leap second. By international agreement, UTC is maintained within 0.7 seconds of the navigator's timescale, UT1. The advancement of precision in time measurement has resulted in redefinitions of the second. Prior to 1956, 1 second was defined as the fraction 1/86,400th of the mean solar day. From 1956 to 1967, it was the ephemeris second, defined as the fraction 1. Oh boy. I'm just going to read the numbers out. 31556925.9747 of the tropical year at 0 hours, 0 minutes, 0 seconds, 31st December, 1899. The second is currently defined as the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-135 atom. Okay. Relativity. Albert Einstein's theory of relativity has caused major revolutions in physics and astronomy during the 20th century. It introduced to science this concept of relativity, the notion that there is no absolute motion in the universe, only relative motion, thus superseding the 200-year-old theory of mechanics of Isaac Newton. Einstein showed that we reside not in the flat Euclidean space and uniform absolute time of everyday experience, but in another environment, curved space-time. The theory played a role in advances in physics that led to the nuclear era, with its potential for benefit as well as for destruction, and that made possible an understanding of the micro-world of elementary particles and their interactions. It has also revolutionized our view of cosmology with its predictions of apparently bizarre astronomical phenomena such as the Big Bang, neutron star, black hole, and gravitational waves. The theory of relativity is a single all-encompassing theory of space-time, gravitation, and mechanics. It is properly viewed, however, as having two separate independent theoretical parts: special relativity and general relativity. One reason for this division is that Einstein presented special relativity in 1905, while general relativity was not published in its final form until 1916. Another reason is the very different realms of applicability of the two parts of the theory: special relativity in the world of microscopic physics, general relativity in the world of astrophysics and cosmology. A third reason is that physicists accepted and understood special relativity by the early 1920s. It quickly became a working tool for theorists and experimentalists in the then burgeoning field of atomic and nuclear physics and quantum mechanics. This rapid acceptance was not, however, the case for general relativity. The theory did not appear to have as much direct connection with experiment as the special theory. Most of its applications were on astronomical scales, and it was apparently limited to adding minuscule corrections to the predictions of Newtonian gravitational theory. Its cosmological impact would not be felt for another decade. In addition, the mathematics of the theory were thought to be extraordinarily difficult to comprehend. The British astronomer Sir Arthur Eddington, one of the first to fully understand the theory in detail, was once asked if it were true that only 3 people in the world understood general relativity. He is said to have replied, "Who is the third?" This situation persisted for almost 40 years. General relativity was considered a respectable subject not for physicists, but for pure mathematicians and philosophers. Around 1960, however, a remarkable resurgence of interest in general relativity began that has made it an important and serious branch of physics and astronomy. This growth has its roots first beginning around 1960 in the application of new mathematical techniques in the study of general relativity that significantly streamlined calculations and that allowed the physically significant concepts to be isolated from the mathematical complexity, and second in the discovery of exotic astronomical phenomena in which general relativity could play an important role, including quasars 1963, the 3 Kelvin microwave background radiation 1965, pulsars 1967, and the possible discovery of black holes 1971. In addition, the rapid technological advances of the 1960s and 70s gave experimenters new high-precision tools to test whether general relativity was the correct theory of gravitation. The distinction between special relativity and the curved space-time of general relativity is largely a matter of degree. Special relativity is actually an approximation to curved space-time that is valid in sufficiently small regions of space-time, much as the overall surface of an apple is curved even through a small region of the surface, even though a small region of the surface is approximately flat. Special relativity thus may be used whenever the scale of the phenomena being studied is small compared to the scale on which space-time curvature, gravitation, begins to be noticed. For most applications in atomic or nuclear physics, this approximation is so accurate that relativity can be assumed to be exact. In other words, gravity is assumed to be completely absent. From this point of view, special relativity and all its consequences may be quote-unquote derived from a single simple postulate. In the presence of gravity, however, the approximate nature of special relativity may manifest itself, so the principle of equivalence is invoked to determine how matter responds to curved space-time. Finally, to learn the extent that space-time is curved by the presence of matter, general relativity is applied. Special relativity. The two basic concepts of special relativity are the inertial frame and the principle of relativity. An inertial frame of reference is any region, such as a freely falling laboratory, in which all objects move in straight lines with uniform velocity. This region is free from gravitation is called a Galilean system. Free fall is motion determined solely by gravitational forces. For example, a dropped object, or one thrown into the air, is in free fall at every point in its trajectory. An object in space is always in free fall. Although influenced by the gravitational fields of many celestial bodies, it may not actually be falling toward any of them. A person in a freely falling vessel is also in free fall and experiences the phenomena of weightlessness. Gravitational effects are the same on both person and vessel, so no acceleration is felt relative to the vessel. The principle of relativity postulates that the result of any physical experiment performed inside a laboratory in an inertial frame is independent of the uniform velocity of the frame. In other words, the laws of physics must have the same form in every inertial frame. A corollary is that the speed of light must be the same in any inertial frame, because the speed of light measurement is a physical experiment, regardless of the speed of its source or that of the observer. Essentially, all the laws and consequences of special relativity can be derived from these concepts. The first important consequence is the relativity of simultaneity, because any operational definition of simultaneous events at different locations involves the sending of light signals between them. Then two events that are simultaneous in one inertial frame may not be simultaneous when viewed from a frame moving relative to the first. This conclusion helped abolish the Newtonian concept of an absolute universal time. In some ways, the most important consequences and confirmations of special relativity arise when it is merged with quantum mechanics, leading to many predictions in agreement with experiments such as elementary particle spin, atomic fine structure, antimatter, and so on. The mathematical foundations of special relativity were explored in 1908 by the German mathematician Hermann Minkowski, who developed the concept of the, quote, four-dimensional space-time continuum, end quote, which includes time and the three spatial dimensions. I had no idea there would be so much discussion of physics in this. I'm enjoying it, don't get me wrong. I just had no idea. Okay. The principle of equivalence and space-time curvature. The exact Minkowski space-time of special relativity is incompatible with the existence of gravity. A frame chosen to be inertial for a particle far from the Earth, where the gravitational field is negligible, will not be inertial for a particle near the Earth. An approximate compatibility between the two, however, can be achieved through a remarkable property of gravitation called the weak equivalence principle, WEP. All modest-sized bodies fall in a given external gravitational field with the same acceleration regardless of their mass, composition, or structure. The principle's validity has been checked experimentally by Galileo, Newton, and Friedrich Bessel, and in the early 20th century by Baron Roland von Eötvös, after whom such experiments are named. If an observer were to ride in an elevator falling freely in a gravitational field, then all bodies inside the elevator, because they are falling at the same rate, would consequently move uniformly in straight lines as if gravity had vanished. Conversely, in an accelerated elevator in free space, bodies would fall with the same acceleration because of their inertia, just as if there were a gravitational field. Einstein's insight was to postulate that this vanishing of gravity in free fall applied not only to mechanical motion but to all the laws of physics, such as electromagnetism. In any free-falling frame, therefore, the laws of physics should, at least locally, take on their special relativistic forms. This postulate is called the Einstein equivalency principle, EEP. One consequence is the gravitational redshift, a shift in frequency f for a light ray that climbs through a height h in a gravitational field given by delta f. Okay, so this is a formula. So we have in parentheses delta f, then slash, so I guess that's divided. F equals gh, another slash, c with a 2 in parentheses. So if you understand all that, good on you. I don't. Where g is the gravitational acceleration and c is the velocity of light. If the light ray descends, it is blue shifted. Equivalently, this effect can be viewed as a relative shift in the rates of identical clocks at two heights. A second consequence of EEP is that space-time must be curved. Although this is a highly technical issue, consider the example of two frames falling freely but on opposite sides of the Earth. According to EEP, Minkowski space-time is valid locally in each frame. However, because the frames are accelerating toward each other, the two Minkowski space-times cannot be extended until they meet in an attempt to mesh them into one. In the presence of gravity, space-time is flat only locally, but must be curved globally. Yeah, well over my head. I'm right there with you on that. Any theory of gravity that fulfills EEP is called a metric theory, from the geometrical curved space-time view of gravity. Because the equivalence principle is a crucial foundation for this view. It has been well tested. Versions of the Eötvös, I know I'm mispronouncing that, experiment performed in Princeton in 1964 and in Moscow in 1971 verified EEP to 1 part in 10, 12 in parentheses, so 10 to the 12th. I don't know. He hasn't used any of the normal power symbol, like if it was 10 to the 12th, it would be 10 with the little tiny 12 up in the corner. He's not using that in this, so I'm assuming 10 with a 12 in parentheses, that's what he means, is 10 to the 12th. I may be very wrong. Gravitational redshift measurements using gamma rays climbing a tower on the Harvard University campus, 1965, using light emitted from the surface of the sun, 1965, and using atomic clocks flown in aircraft and rockets, 1976, have verified that effect to precisions of better than 1%. General relativity. The principle of equivalence and its experimental confirmation reveal that space-time is curved by the presence of matter, but they do not indicate how much space-time curvature matter actually produces. To determine the curvature requires a specific metric theory of gravity, such as general relativity, which provides a set of equations that allow computation of the space-time curvature from a given distribution of matter. These are called field equations. Einstein's aim was to find the simplest field equations that could be constructed in terms of the space-time curvature and that would have the matter distribution as source. The result was a set of 10 equations. This is not, however, the only possible metric theory. In 1960, C.H. Brans and Robert Dicke developed a metric theory that proposed, in addition to field equations for curvature, equations for an additional gravitational field whose role was to mediate and augment the way in which matter generated curvature. Between 1960 and 1976, it became a serious competitor to general relativity. Many other metric theories have also been invented since 1916. I know he's got a point in all this physics stuff. I just hope he gets to it in the 3rd chapter. An important issue, therefore, is whether general relativity is indeed the correct theory of gravity. The only way to answer this question is by means of experiment. In the past, scientists customarily spoke of the 3 classical tests proposed by Einstein: gravitational redshift, light deflection, and the perihelion shift of Mercury. The redshift, however, is the test of the equivalence principle, not of general relativity itself, and 2 new important tests have been discovered since Einstein's time: the time delay by I. Shapiro in 1964 and the Nordtvedt effect by K. Nordtvedt Jr. in 1968. The confirmation of the deflection of starlight by the sun by the solar eclipse expedition of 1919 was one of the triumphant moments for general relativity and brought Einstein worldwide fame. According to the theory, a ray of light propagating through the curved space-time near the sun should be deflected in direction by 1.75 seconds of arc if it grazes the solar surface. Unfortunately, measurements of the deflection of optical starlight are difficult, in part because of the need for a solar eclipse to obscure the light of the sun, and repeated measurements between 1919 and 1973 yielded inaccurate results. This method has been supplanted by measurements of the deflection of radio waves from distant quasars using radio telescope interferometers, which can operate in broad daylight. Between 1969 and 1975, 12 such measurements ultimately yielded agreement to 1%, with a predicted deflection of general relativity. The time delay effect is a small delay in the return of a light signal sent through the curved space-time near the sun to a planet or spacecraft on the far side of the sun and back to Earth. For a ray that grazes the solar surface, the delay amounts to 200 millionths of a second. Since 1964, a systematic program of radar ranging to the planets Mercury and Venus, to the spacecraft Mariners 6, 7, and 9, and to the Viking orbiters and landers on Mars, has been able to confirm this prediction to better than half of 1%. The Nordtvedt effect is one that does not occur in general relativity, but is predicted by many alternative metric theories of gravity, including the Brans-Dicke theory. It is a possible violation of the equality of acceleration of massive bodies that are bound by gravitation, such as planets or stars. The existence of such an effect would not violate the weak equivalency principle that was used as a foundation for curved space-time, as that principle applies only to modest-sized objects whose internal gravitational binding is negligible. One of the remarkable properties of general relativity is that it satisfies EEP for all types of bodies. If the Nordtvedt effect were to occur, then the Earth and Moon would be attracted by the Sun with slightly different accelerations, resulting in a small perturbation in the lunar orbit that would be detected by lunar laser ranging, a technique of measuring the distance to the Moon, using laser pulses reflected from arrays of mirrors deposited there by Apollo astronauts. In data taken between 1969 and 1976, no such perturbation was detected, down to a precision of 30 centimeters, 1 foot, in complete agreement with the zero prediction of general relativity and in disagreement with the prediction of the Brans-Dicke theory. Oh, hey, I got a notice for an ad break coming in 20 seconds. That's the first time I have noticed that happening. So I'm going to shut up in 10 seconds because y'all aren't going to be able to hear me. And there we go. Okay, ad break ended. All right. So, okay, I thought when the notice came up that the ad was starting, or was going to start in 10 seconds or 30 seconds, but it was actually going for 30 seconds. So I was sitting there jabbering away. Anyway, a number of secondary tests of more subtle gravitational effects have also been performed during the last decade. General relativity has passed every one, while many of its competitors have failed. Tests of gravitational radiation and inertial frame dragging are now being devised. One experiment would involve placing spinning objects in Earth orbit and measuring expected relativistic effects. Cosmology and time. Really? I got that many pages left to go? Oh, we got a bunch of pictures coming up. Wow. Okay. Cosmology and time. One of the first astronomical applications of general relativity was in the area of cosmology. The theory predicts that the universe could be expanding from an initially condensed state, a process known as the Big Bang. For a number of years, the Big Bang theory was contested by an alternative known as the steady state theory, based on the concept of the continuous creation of matter throughout the universe. Later knowledge gained about the universe, however, has strongly supported the Big Bang theory as against its competitors. Such findings either were predicted by or did not conflict with relativity theory, thus also further supporting the theory. Perhaps the most critical piece of evidence was the discovery in 1965 of what is called the background radiation. This quote-unquote sea of electromagnetic radiation fills the universe at a temperature of about 2.7 K, 2.7 degrees Celsius above absolute zero. Background radiation had been proposed by general relativity as the remaining trace of an early hot phase of the universe following the Big Bang. The observed cosmic abundance of helium, 20 to 30% by weight, is also a required result of the Big Bang conditions predicted by relativity theory. In addition, general relativity has suggested various kinds of celestial phenomena that could exist, including neutron stars, black holes, gravitational lenses, and gravitational waves. According to relativistic theory, neutron stars would be small but extremely dense stellar bodies. A neutron star with a mass equal to that of the Sun, for example, would have a radius of only 10 kilometers, 6 miles. Stars of this nature have been so compressed by gravitational forces that their density is comparable to densities within the nuclei of atoms, and they are composed primarily of neutrons. Such stars are thought to occur as a byproduct of violent celestial events such as supernovae and other gravitational implosions of stars. Since neutron stars were first proposed in the 1930s, numerous celestial objects that exhibit characteristics of this sort have been identified. In 1967, the first of many objects now called pulsars was also detected. These stars, which emit rapid, regular pulses of radiation, are now taken to be rapidly spinning neutron stars, with the pulse period representing the period of rotation. Piece of trivia: the very first pulsar discovered was called LGM1, Little Green Men 1. Black holes are among the most exotic of the predictions of general relativity, although the concept itself dates from long before the 20th century. These theorized objects are celestial bodies with so strong a gravitational field that no particles or radiation can escape from them, not even light, hence the name. Black holes most likely would be produced by the implosion of extremely massive stars, and they could continue to grow as other material entered their field of attraction. Some theorists have speculated that supermassive black holes may exist at the centers of some clusters of stars and of some galaxies, including our own. While the existence of such black holes has not been proven beyond all doubt, evidence for their presence at a number of known sites is very strong. I think they have actually proved black holes exist now. This was written in 1999, so 23 years later, I think I actually heard Neil deGrasse Tyson or something. I think he was talking about how they have been confirmed. In theory, even a relatively small mass could become a black hole. The mass would have to be compressed to higher and higher densities until it diminished to a certain critical radius, the so-called event horizon, named the Schwarzschild radius because it was first calculated in 1916 by German astronomer Karl Schwarzschild. His calculations apply to a non-rotating object. The figures for a rotating object were developed in 1963 by New Zealand mathematician Roy Kerr. For an object having the mass of the Sun, the event horizon would be approximately 3 kilometers, 2 miles. Scientists such as the English theoretical physicist Stephen Hawking have speculated that tiny black holes may indeed exist. The concept of gravitational lenses is based on the already discussed and proven relativistic prediction that when light from a celestial object passes near a massive body such as a star, its path is deflected. The amount of deflection depends on the massiveness of the intervening body. From this came the notion that very massive celestial objects, such as galaxies, could act as the equivalent of crude optical lenses for light coming from still more distant objects beyond them. An actual gravitational lens was first identified in 1979. One phenomena predicted by general relativity has not yet been substantially verified. However, the existence of gravitational waves the existence of gravitational waves. Gravitational waves would be produced by changes in gravitational fields. They would travel at the speed of light, transport energy, and induce relative motion between pairs of particles in their path, or produce strains in more massive objects. Excuse me. Astrophysicists think that gravitational waves should be emitted by dynamic sources such as supernovae, massive binary or multiple star systems, and black holes or collisions between black holes. Various attempts, unsuccessful thus far, have been made to observe such waves. A more fundamental matter confronting general relativity is that of the attempt being made by physicists to unite gravitation with quantum mechanics, the other paradigm of modern physics. This search for some unified field theory is the major task of workers in quantum cosmology. He talked about unified field theory in the first chapter a bit. The clock paradox. The clock paradox is the best known example of a class of paradoxes that have been devised in order to test the logical consistency of the special theory of relativity, or, in some cases, in attempts to discredit the theory. To formulate such paradoxes, one imagines a, quote, thought experiment, end quote, for which the theory apparently makes one prediction when the experiment is analyzed one way, but makes a contradictory prediction when it is analyzed a different way. It is generally agreed, however, that all such paradoxes can be resolved quite simply by a correct application of the principles of relativity. A simple version of the clock paradox is stated as follows. Two identical twins, Charlie and Kip, part company. Charlie remaining at home and Kip piloting a rocket ship at constant velocity to a distant location. Upon reaching his destination, Kip reverses direction and returns home at constant velocity. From Charlie's point of view, Kip's clocks have run more slowly than his because of the relativistic time dilation resulting from Kip's velocity. Therefore, Kip should return younger than his former twin. This is a surprising prediction, and although true, it is not in itself paradoxical. The apparent paradox occurs when the situation is analyzed from Kip's point of view. From Kip's viewpoint, it is Charlie who moves with constant velocity away and then back. Therefore, his clocks should run more slowly than Kip's, and it is Charlie who should be younger. Both predictions cannot be correct, hence the apparent paradox. The simplest way to resolve the paradox is to realize that the two situations are not really symmetrical. Charlie remains in an inertial frame, or non-accelerating environment in which Newton's laws hold, throughout the experiment, whereas Kip must undergo an acceleration in order to halt his rocket ship and reverse its direction. During this acceleration, he notes that Charlie's clocks speed up and in fact overtake his clocks. This he understands by carefully carrying out special relativistic calculations using a sequence of inertial frames that at each instant during his acceleration are momentarily at rest with respect to him. Because these frames have different velocities, he must take into account the systematic difference in the way that clocks are synchronized from one frame to the next. An alternative way to understand the speed up of Charlie's clocks is to realize that because of the principle of equivalence, Kip cannot distinguish his accelerated frame from one at rest in a uniform gravitational field, in which there is an apparent quote-unquote gravitational blue shift, increasing the rate of Charlie's clocks. The final conclusion, both observers agree that Kip must return younger than Charlie. An experiment performed in 1966 in an accelerator at CERN in Geneva, Switzerland, verified this result, in which the travelers were unstable elementary particles called mu mesons, confined by means of magnetic fields to move in circular paths, with velocities 99.6% the speed of light. The returning muons were found to be younger, that is, to have decayed more slowly, than muons at rest in the laboratory. Thus, both experiments and a correct application of theory verify that there is no clock paradox. All right, so we've got a couple of pictures. Then we've got wow, these pages are so thin. I'm having trouble even opening. Okay, then we've got 5 more pages and 2 more pages of pictures. So here we go. What is this one? The figure illustrates the curvature of space-time with a two-dimensional plane representing 3-dimensional space. The lines are the path light takes as it travels through space. A massive body warps space, causing the path of light to bend. Energy also causes space to curve, as Einstein's theory of general relativity describes, from Tapping the Zero-Point Energy by Moray B. King. So here is that one. It's this top part. So I'll try to get in there. All right. So the first one is light. The second one with the ball there is the gravitation curving the light. Okay. The second picture here is from Time Mechanics by Paul Naheen. Stationary particles, constant speed particle, accelerating particle. Okay, so it's an X, Y, and T axes, I guess. World lines of 3 particles. Okay, so that's this one. So this, the far one, this one on this side, is the T, is labeled T, and then this one is labeled X, and of course the one here is Y. Okay, getting back to space-time continuum. As mentioned above, the space-time continuum is a concept associated with the theory of relativity. It replaced the Newtonian concept of space at a separate absolute time. In Newtonian mechanics, any event can be associated with a location in space and with a moment in time, t. The coordinates chosen are arbitrary, but 2 quantities are independent of the choice. The spatial distance between 2 events, delta I, and the difference in time between them, delta t, with the equivalent with delta t, period. With the advent of relativity, however, it became clear that time depends on velocity and that delta I and delta t are no longer separately invariant. Delta I undergoes the Fitzgerald-Lorentz contraction, and delta t undergoes time dilation. A new quantity, delta S, is invariant instead. This quantity, known as the quote-unquote line element, or the quote-unquote invariant interval, is related to the other quantities through a quadratic expression involving the speed of light. The quantity delta S is now the invariant measure of intervals between events, and the term metric, from the Greek word for measure, often refers to the quadratic expression for delta S squared. In general relativity, the space-time metric is more complicated and corresponds to curved space-time. The Fitzgerald-Lorentz contraction is an effect first postulated in 1892 by George F. Fitzgerald and amplified in 1895 by Hendrik A. Lorentz. It was proposed in an attempt to explain the null result of the Michelson-Morley experiment performed in 1887, which measured the time taken for a light beam to travel a distance d and back when the direction of motion of the beam was parallel to the supposed direction of motion of the laboratory or observer, through the quote-unquote ether. The time was compared with that for the same trip when the laboratory moved perpendicular to the light's direction. In this case, the laboratory's motion was the Earth's motion through space. The ether was the medium through which light was presumed to travel with speed c. According to classical theory, the time taken for both round trips should be different. The Michelson-Morley experiment, however, demonstrated no difference in travel times. Fitzgerald suggested that if the length of the parallel arm d were contracted to dx, the square root of 1 minus v to the second divided by c to the second, where v is the speed of the laboratory, while that of the perpendicular arm remained unchanged, the prediction would agree with the experiment. Lorentz later proposed a model for matter that incorporated this effect. He stated that the atoms and molecules that compose matter would, under the effect of motion, be compressed along the direction of motion. It would be impossible to measure this deformation. A ruler placed alongside a speeding object would be similarly shortened. Albert Einstein showed in his theory of relativity that the contraction was a fundamental consequence of the assumption that the speed of light is the same in all reference frames. The effect is only significant at relativistic speeds, or speeds that are a sizable fraction of the speed of light. The world line. A world line is a path through space-time. It is a mathematical concept used in physics to describe the motion of particles or other objects. A world line gives a more informative description than a path through space, because each point along the world line indicates both the time and the position of the object. To understand the distinction between a curve drawn on a map to indicate the path of an aircraft over the surface of the Earth. To understand the distinction, consider a curve drawn on a map to indicate a path of the aircraft over the surface of the Earth. If the altitude is marked along the curve, the path is described in three-dimensional space. If the time that the aircraft passes each point is also indicated, the description is of the world line, or path, in the fourth-dimensional space-time continuum. Two world lines intersect only if they cross the same position at the same time. Physicists use world lines to describe how particles move, collide, and recoil from each other by their fundamental interactions. Metric theories of gravitation, for example, such as Einstein's general relativity, predict that freely falling particles move along geodesics, the paths closest to straight lines in curved space-times. Real particles with non-zero rest masses travel slower than light and move on time-like geodesics, which give the longest time measured between two events. Other world lines between the same two events experience less elapsed time by the clock paradox. Okay. A motion in which, time reversal invariance. A motion in which events appear in reverse order is said to be time reversed with respect to the original motion. If some motion is possible according to known physical laws, then the time-reversed motion is almost always possible. This possibility is true for motions caused by gravitational and electromagnetic forces. It is therefore said that these laws exhibit time reversal invariance and have time reversal as a basic symmetry. For example, it would be unusual to observe a real process in which an egg broken on the floor collects itself and flies up whole into a person's hand, as in a movie run backward. Nevertheless, according to known physical laws, such a process is not impossible, although it is too unlikely to expect it actually to happen. Movies of simpler processes, however, such as a spinning top or a vibrating bell, appear nearly normal when run backward. The basic natural laws governing most elementary processes are invariant under time reversal. Most natural processes themselves, however, do not appear to be symmetric under time reversal. This result is because of the complexity of macroscopic systems containing many particles. For example, consider a vessel divided into two parts by an airtight partition. One part contains air and the other is evacuated. If the partition is removed, air will expand into both parts of the vessel until both parts of the vessel are filled. To obtain the time-reversed motion in which all the air filling the vessel streams to one side, the velocities of all the particles would have to be reversed, an impossible task. The complexity of this system results in an extremely small likelihood that the time-reversed motion could occur. Complex systems generally develop in time toward a more probable state. This increase in likelihood is relative to an increase of entropy of the system. On the subatomic level, there are additional forces to consider with respect to time reversal invariance. The strong nuclear force responsible for binding atomic nuclei and the weak force responsible for the radioactive decay of such particles as the neutron. The neutron decays into a proton, an electron, and an antineutrino. The motion that is time reversed with respect to the neutron decay is represented by a formula in which an antineutrino, an electron, and a proton come together to form a neutron. In order for the time reversed reaction to correspond to the original decay, the energies of the incoming particles must be the same as those of the previous outgoing particles, and the velocities and spins of the particles must be reversed. This process is possible, although unlikely. Experiments with elementary particles test time reversal invariance by observing processes in which elementary particles are produced, interact, and decay. Time reversal invariance appears to be a valid symmetry for all processes except in the weak decay of kaons. Wow. I'm not done yet. There are 3 more pages to read, plus a couple pictures, but I had no idea it was going to be like this. Let's keep going. In the fall of 1998, it was reported in the worldwide press that a special experiment had taken place at Sussex University in the England that literally froze time. Said newspapers in London at the time, quote, "For a few seconds last month, the coldest spot in the universe was in Brighton, while the temperature outside hovered around 20 Celsius on September 22nd. Inside Malcolm Bouchier's optics lab in Sussex University, it was a few hundred billionths of a degree above the coldest temperature possible, negative 273 Celsius." Where did my quote end? It didn't. Okay. Quote, "When Bouchier and his team dropped 100,000 atoms down to nano-Kelvin temperatures, they were not merely trying to get into the Guinness Book of Records. This is a step on the road to making the world's most sensitive measuring instruments, so sensitive that they might help to unlock the secrets of gravity." Again, they didn't end the quote, and they started another one. "The Big Freeze created a Bose-Einstein condensate, BEC, which occurs when atoms lose almost all their energy. In this state, an extraordinary thing happens. Each atom loses its individuality. They spread out into each other, forming a blob that behaves like one enormous superatom. Quote, "It's an object that obeys the laws of quantum mechanics, yet it's large enough that you can take a picture of it," end quote, says Bouchier. Quote, "Albert Einstein and Satyendra Bose predicted such a thing would happen at ultra-low temperatures more than 70 years ago, but it wasn't until 1995 that a Colorado research group first made a BEC. Quote, "This represents the tightest control you can have over atoms," end quote, says Bossier. Quote, "We should be able to build devices that will be extremely sensitive to anything that affects an atom's energy levels, and that includes gravity," end quote. And another quote, "An understanding of just how gravity works will elude researchers, and an instrument to measure its subtle effects will be vital in unearthing its secrets. The next stage is about to begin. Sussex Center for Optical and Atomic Physics has already produced magnetic mirrors, which bounce atoms around in the same way that mirrors bounce laser light. Bossier will soon be dropping the BEC onto a magnetic mirror to check that it bounces like normal atoms." And again, they didn't end the quote. They keep starting every new sentence with a quote without ending them. That's annoying. So this is another one, quote, "If it does, the team will try to build an atom interferometer. Lasers provide highly accurate interferometers because the photons of the tiny packets of light in their beams are locked in step. This provides a way to measure tiny dimensions. Split a laser beam in two, and the relative length of the two different beam paths can be measured. Those in one half are slightly out of step with the others. This has led to highly sensitive instruments such as laser gyroscopes." And again, quote, "In a BEC, the atoms, like the photons in a laser beam, are locked together, which will provide an even more accurate interferometer. Creating a BEC involves two stages. First, put rubidium vapor into an evacuated flask. 6 lasers are arranged around the flask with their beams intersecting at the center. To a normal moving atom, this is like wading through what the researchers call optical molasses. The atom loses energy, slows down, and cools to around 1/1000th of a degree above absolute zero, or negative 273 Celsius. Cold, but not cold enough. The stars are constantly adding energy to the atoms, so they are turned off and a specifically shaped magnetic field is turned on. This holds the atoms as if it were a deep-sided bowl. The atoms with the most energy steal some from the others and escape from the top of this magnetic trap. Thus, the remaining atoms get colder. Eventually, an atom reaches the point at which it can move into its lowest quantum state, the ground state. The nature of these atoms is such that others quickly follow. Quote, "When it is cold enough so that there is some chance of having one atom in the ground state, many of the others scatter into that same ground state," says Bossier, end quote. The result is a quantum blob a few microns in diameter. It may not sound like much, but it contains the future, Bossier reveals. And Bossier is then quoted as saying, quote, "This field is really exploding. 500 or 600 papers of them, theoretical, have been written on it in the last 3 years. This is going to do for atoms what lasers did for light," end quote. Indeed, some of the secrets of time travel may have been unlocked by Bossier and his team. The technique of splitting a laser beam in two and the use of laser gyroscopes may ultimately lead us to the practical time travel device that many are looking for, as we shall see in later chapters. Meanwhile, let us look back in time, 100 years or so, at the beginning of our own era's interest in time travel, for it seems that those who are interested in time travel are likely to meet time travelers. And then he's just got a note, the material in this chapter is largely from the Grolier Multimedia Encyclopedia, and then he gives some reference material. So here we go, the two pictures that end the chapter. A drawing of the 1896 California airship that was widely circulated in newspapers at the time. Note the powerful searchlight that the airship was described as having. So here we go. I'll start out here and then move in for more detail here. The airship, the searchlight. Okay. And then the next picture is the next page is, there's a lot of text here. So I'll go ahead and read it. It's descriptions of the airship were within the general framework of cigar-shaped and metallic, but varied as to the kinds of appendages seemingly attached to the body. Wings, propellers, and fins were all described by different witnesses. Both daytime and nighttime sightings were reported, and in the case of the latter, brilliant lights were seen. Reports of sightings continued through May 1897 and came from almost every state of the Union east of the Rockies, with a concentration in the Midwest. The Encyclopedia of UFOs, Ronald D. Story, Editor 8/211. And then there's the picture, and then some more text here. Another wave of airships was reported from New Zealand during 1909. For 6 weeks from late July to early September, hundreds of people observed cigar-shaped airships over North Island and South Island. Sightings occurred in daytime and nighttime. The early 20th century was a time of experimental aircraft. The dirigible balloons being built by Graf Ferdinand von Zeppelin in Germany were still in an early stage of development, and so were the balloons being tested in France. These craft could not possibly have found their way to New Zealand. So, and then the picture itself, a great wave of UFO sightings occurred in California in the late 1800s. This story and illustration appeared in a San Francisco newspaper on November 22nd, 1896. So it's the same picture, just in context from the, sorry, this way, from the newspaper. So there's, let me see if I can turn that a little bit. Come in so you can read the top. And in that picture, saw the mystic flying light. Oaklanders who believe in airship, an airship hovered over them. So there you go. And that is the end of that chapter. And that other picture is time bandits from the 1800s. I'll go ahead and show you that. But that is the cover page for Time Bandits from the 1800s, which will be our next chapter next time. And it starts with another picture I'll show you next time. So, alrighty then, folks. Hopefully that's gotten us past all of the physics, so we can get on to, well, Time Bandits from the 1800s. Sounds like it's going to get into actual accounts and claims. So, yeah. All right. That'll be that. I'm not going to game tonight. We'll get back to this on Sunday. So, I will. I am going to raid somebody tonight. So please stick around just for a few minutes. Give them 5 minutes of your time. You don't have to stick around, but give them a few minutes. Old World Charm is playing Baldur's Gate 3, and I have not seen it yet, so I'm going to take us over there. So please stick with me for a minute. I'm going to start the end screen and then start the raid. Thank you all for coming in and listening.
Because I have seen I have known about the I didn't have anything to say. Follow your heart, don't take. If you leave it behind, someone will bring. I left you my heart. What did you do? You used to get abused. You left me soft. Was it push this person out? You have no answers. Don't know without you. How will I disarm attack?